Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, special permutation. The problem is very interesting. In particular, I will be trying to help any beginner understand what DP with bitmasking is, and I am very sure if you stick till the end, you will be able to understand what DP with bitmasking is and apply that concept in any future problem as well. So with that, let's get started. The problem states that you are given a zero indexed array nums with n distinct positive integers. Notice the word distinct. We'll look at the problem will completely change if this distinct is not there, and I would strongly encourage you to think about why this distinct is important after we have thought about the solution. Now, a permutation is called special if for every I this condition is satisfied. Either num psi should divide num psi plus 1 or num psi plus 1 should divide num psi. Now you need to return the total number of special permutations, and since the answer could be very huge, you have to return it modulo 10 to the power n plus 7. Right? Now let's say this is the array 2, 3, 6. So there are total 6 possible permutation of this particular array. Among those 6 permutation, 2 of them are good, 362, 263. Now why they are good, let's talk about it. So for each index, this should be satisfied. So if you see, for the first index I equals to 0, num psi and num psi plus 1, num psi plus 1 actually divides num psi, right? So this for I equals to 0, the condition is satisfied. Now for I equals to 1, again nums of I plus 1 divides nums of I. So again the condition is satisfied. So because the condition is satisfied for all I from 0 to n minus 1, this permutation is a good permutation. Now similarly, this permutation, if you think about it, for I equals to 0, again num psi plus 1 divides num psi. For I equals to 2, again num psi divides num of I plus 1. So both the permutations are good, and only these two are good. If you try any other possible permutation, let's say 2, 3, 6 itself is a possible permutation, but this is not a good permutation, because if you see, for I equals to 0, the condition is not satisfied. Neither 2 divides 3 nor 3 divides 2, right? So only 2 permutations are valid or good, and hence 2 is the answer. So hope the problem statement is clear. Now how to solve this? Again, let's start with a very brute force approach. Let's say this is the given array. Now what exactly will be the brute force solution? You will say, okay, I will find out every possible permutation. For each permutation, I will see whether the permutation is good or not by applying the same algorithm that we just discussed. For every I will see whether nums of I divides nums of I plus 1 or the other way around. And if for all the permutations for which this condition is satisfied, I will just increment a result and return that as an answer. So everything is good. Now I would strongly encourage you to pause the video and try to find out all the permutation, or try to write a code for finding out all the permutations of a given array, because that's what you said you will be doing in the brute force solution, right? So strongly encourage you to pause the video and try to code that, or write pseudocode at least by yourself. So hope you have thought about it. So how exactly will you find out the number of permutation? The easiest way is to use recursion. Now how recursion? Let's think about it. So let's say you have 5 spaces, right, to fill. Now for the first one, which all elements you can put? You can put any of 8, 4, 24, 3 and 21, right? You can put any of these. Let's say you put 4, right? So if you put 4 here, the first element is now fixed, right? Now you have to fill the remaining 4 elements with the remaining 4 elements here, right? So you can simply assume that 4 was never there, and now you have to figure out what is the number of permutations, or what all are the number of permutation for 8, 24, 3 and 21. So isn't this problem exactly similar to the original problem? Original problem was, give me the number of permutation of this array which contain 8, 4, 24, 3, 21. Now we are saying that give me number of permutation, like after we have fixed 4 here, let's say we are saying give me number of permutation for 8, 24, 3, 21. So this problem is exactly similar to the previous one with just reduced constraint. Previously there were 5 elements, now there are 4 elements. So hope you can see the recursion here. So let's try to write out this recursive formula. So again, first thing would be that which index we are trying to fill, right? Now what's next? So we, for the remaining elements, we need to, so okay, which we, let's say this is I, we are trying to fill this particular index. Now which all elements you can put here? You can't put everything that was there in original array, right? Because there might be some elements which you have already used, so you have to put something which was remaining. So to figure out which one is remaining, you need something else in your function as well. So you need to maintain two things: first, the index which you are filling, and second, what all elements are remaining to be filled, right? So this is how the pseudo code would look like. You will say, okay, I have the index and the remaining elements. This remaining elements is an array which contains all the remaining elements. Now for every index, for this particular index, what you will do, you will try out every possible element in this remaining element, right? And for each of these possibilities, you will figure out what is the how many permutations are possible for the next set of elements. So let's say you fixed 4 here, so you will figure out, okay, how many permutations are possible for this particular for this all numbers, right? So let's say you get permutation is 8, 24, 21 and 3. So what you will do, you will say, okay, I will prepend 4 to this permutation and I will get a permutation of size 5, right? So that's what we are doing. We are saying, okay, I will get all the possible permutation for the remaining elements. Now this will be an array of array, right? And I will prepend next to each of these vector, and finally this will be my new set of permutation, right? So you don't need to worry about this particular thing, you will get when you are trying to implement it. But the crux is, we are applying recursion with two states, index and remaining elements. Remaining elements, we are, every time we put one element, we update remaining elements with the elements except the current used elements, right? So we have found out the number of like all the permutations, but the original problem was figure out how many good permutations are there. We don't need to actually figure out all the permutations. So let's just try to modify this a bit to fit in the original problem. So original problem was, we just need to figure out how many good permutations are possible with this. So how exactly will you figure out the count from this particular recursion is the problem now. I would again encourage you to pause and try to think by yourself. So the only thing that will now matter is, you don't need to figure out all the permutation, right? Because you don't need to figure out what is the end result, because if you want to figure out that, you need to actually know all the permutations. So you need to actually run this entire algorithm and figure out all the list of permutations and then apply the algorithm. But what we need is, we want to actually figure out the count within this particular recursive function itself. So for that, what we are trying to do is, we'll say what matters. So let's say you pick, you put 8 here, so there are 5 spaces, you put 8 here. Now at the next element you are putting 3. So can you put 3 is the question. So you can't put 3 if either 3 doesn't divide 8 or 8 doesn't divide 3, right? So for every element that you are putting, one more restriction is there. Previously there was one restriction that it should belongs to the list of remaining elements, but now there is one more restriction. The restriction is that the element should also divide the previous element, or the previous element should divide the current element. So for this particular thing, if you remember previously, we for getting one constraint, we introduced remaining element as a state. Now we need one more constraint, so we introduce one more state in the recursion, which is the last element, because we know to actually figure out whether I can put a particular element here or not, I need to see whether last element divides me or I divides the last element, right? So now everything is exactly same. Only thing that changes, if index is n, we return 1. Basically it's saying that we have filled all the n elements, so we found one valid permutation, right? Otherwise I will try to put next in the current index, right? Now if next is good, then only I will move forward. Otherwise I will try the next, I will skip the current element, right? Now what this is good will just say whether this element divides next or next divides this element or not. So whether a modulus b is 0 or b modulus a is 0. If either of them is true, is good will return true, otherwise it will return false. So basically we are saying that if it is not good, I will not pick the current element, and instead I will try the next possible set of elements, right? So this is the only constraint that we have added here, and now we can simply get the answer by just running this particular recursive function, how many good permutations are possible, right? Now what is the time complexity of this entire thing? Notice that we have, like, how to find time complexity. First of all, you can say, okay, I will like we are iterating over all possible permutations, so there are n factorial permutation, and for each permutation I am also figuring out whether it is good or bad, and for that I am iterating over all the elements, and hence the complexity is n factorial into n. So that is good, but we need to optimize this, because this will surely not work, because n is 14, so 14 factorial into n is very huge. So how to optimize this? The very standard way to optimize any recursive function is to do memoization. Now what memoization you will do? You will say, okay, if I have calculated the answer for this particular state, then I will not recalculate it, instead I will return it from the cache, right? So the complexity then would be number of states multiplied by what you are doing in each state, right? So what first of all, let's figure out what we are doing in each state. So inside each state we are iterating over all the remaining elements. So how many remaining elements can be there in the worst case? Order n, right? Now how many states are possible? So how many states are possible is number of distinct value of index multiplied by number of distinct value of last element multiplied by number of distinct value of this particular array. So first one is simple, the number of distinct value of index would be n, number of distinct value of last element would again be n, right? And finally number of remaining elements. So how many remaining elements can be there? So this is an array, right? And each element here can get up to 10 to the power 9, let's say, right? Or let's take the original example, like here it says that each element can go to 10 to the power 9. So in this particular array there can be n elements, each element can go up to 10 to the power 9. So in total you can have 10 to the power 9 for each element, and there are total n elements that can be possible in this particular array. So this is the number of states that you will have, and surely this will not pass. This is more bad than the original time complexity. Now you have to optimize this. So in this particular thing, what exactly will you optimize? We have to optimize this particular thing, because n is something we can afford, because n is very small. So how to optimize this? Notice that this is like why 10 to the power 9 comes, because each element can be up to 10 to the power 9. So can we reduce what will be there in each element in this remaining element? I would encourage you to think about it. One very quick observation could be, okay, I will, instead of maintaining the actual elements, I will maintain the indexes. So if you maintain the indexes, this 10 to the power 9 will be brought down to n. So the complexity would be n to the power n. Even that is very huge. We have to optimize this as well. So again, think about it for a moment and then move forward. So we have to optimize the number of, or basically what exactly can go in this remaining elements. So currently it has n to the power n distinct values, and we have to optimize this. So note that we can actually, instead of like, why this n is coming, because we are maintaining the indexes one by one, right? So instead of this, if we can maintain a array of booleans, so we can say okay, there are n elements here, so this to the power n will continue, so there are n elements that will continue, but instead of maintaining that which all elements are there, we will just maintain whether 0th index is there or not. So this is a boolean array, everything will be 0 or 1. So we are saying that whether first index is there or not, or is present in the remaining elements or not. So by doing that, we have reduced this n to the power n to 2 to the power n as well. Okay, just to reiterate, previously it was n to the power n because you are maintaining that okay, 1, 3 and 4 is remaining, right? Now because the length of this array can go up to order n, and each element here can itself go up to order n, the complexity was order n to the power n, right? Now we are saying that okay, the array can go n, that we can't do anything about. So the array can be up to n. So let's fix the array size n, and we'll say for every element will store either it is present or not, right? So this n will be reduced to 2. So that's what the complexity would be now. So the complexity would now become, instead of n to the power n, it is 2 to the power n. So the complexity is n into n square into 2 to the power n. This is the number of states multiplied by n, right? So let's quickly look at the pseudo code. The pseudo code will be exactly similar. Only thing that we have changed is instead of remaining elements, we now have elements taken. So this is a boolean array, and previously we were iterating over all the elements here. Now we will iterate over all the index, and we'll check if it is present or not. If it is not present, we'll simply continue. If it is present, it means I can put it, and now rest of the things will follow as is. So we'll check if it is good or not. If it is good, then I can take it. So because I have taken it, I will just mark it as true and call the same function again with the next set of parameters. If it is not good, we'll simply continue from here, right? So hope this entire thing makes sense. This part is still order n, and number of states is now order n square into 2 to the power n. So this entire thing would pass the given time constraint. Now if you haven't understood anything up till this part, I would strongly encourage you to rewind the video and try to understand the part that you have to understand. Next section we'll just be looking at one small optimization that actually translates to what Bitmask DP is. So notice that you are memoizing this thing, right? So for memoization you usually use a 2D array or 3D array, right? But because this third argument itself is an array, you can't use a 2D or 3D array. Instead you have to use a map or an unordered map or anything of that sort. Basically you are saying that you have these 3 states with you, and each of these 3 states will correspond to a particular integer, right? Now maintaining this particular map could be tedious, right? So instead what we usually do is this notice that this array is a boolean array, right? So this would look something like this, 1 0 0 0 1, right? So what this is looking like, this is nothing but, you can say that okay, this is a binary representation of some number. So you can replace this entire thing with its decimal format. You can say okay, this number is 2 plus 4 plus 16. So you can say this number is 22. So whenever you see 22, you will know that you can actually transform 22 into something like this, right? So instead of passing this entire boolean array, you will pass 22, and inside this function you can convert 22 back to this boolean array, right? So that would not affect anything with the number of states. Number of states will still be 2 to the power of n. But what that actually help us is, instead of maintaining this complex data structure, we can simply maintain a 3D array now, because the third argument is again an integer, right? So that's what Bitmask DP is. We call this third argument as mask, which just says whether a particular index is set or not. So we are just iterate like this. This is exactly similar to the previous one. Instead, we just, wherever we were using elements taken, will now use mask. So what we are doing is, you can simply convert this mask back to elements taken inside this array, or you can directly play with mask itself if you know about bit manipulation. So if you are new to this concept, I would encourage you to actually convert this mask back to elements taken and apply this entire algorithm again. Otherwise, if you know about bit manipulation, you might find this bit easier, that what we are checking here is whether element is taken or not. So to figure out whether a particular bit or whether the ith bit is set or not, we can simply do a AND with one left shift I, and if it is greater than 0, it means it is set. If it is not greater than 0, it means it is not set. So that's what we are doing. And then this is the second condition that was previously like this, and this is the third condition again. This is the third condition where we are calling the function. So previously we were making this particular ith element as true. Now to make this ith element true, we have to actually set the ith bit, and this is the way you set the ith bit in a binary representation of any number. So again, if this part or this part is looking a bit tedious for you, you can simply convert this mask back to elements taken by a simple decimal to binary conversion, and you can directly use this elements taken here, right? So finally, this algorithm, as discussed, will work in order 2 to the power n into n square. These are the number of states, and inside each of these you are doing an order n operation, right? Now there is a very small optimization that you can make here that will help us remove one n from here completely, right? So again, think about it. One of these arguments is something that we don't need. So hope you have thought about it. So if you see, this index is something that we can also figure out from this mask. Basically we can say, if previously we are checking whether index is equals to n, and that's why that's the only use of index. You can see anywhere else we haven't used index at all. So instead of doing this, or basically we are maintaining index just for checking whether everything is filled or not, so we can simply use mask or elements taken as well. So elements taken, basically you can say whether every bit is set or not, or whether every position in this array is set or not. So to check whether every bit is set or not, you use something like this. And once you know that every bit is set or not by using mask, now index is of no use. So you can simply drop index, and because you have dropped index, number of states is now reduced to order n into 2 to the power n, and that will be the, that is number of states, and inside each of these states you are iterating over all the elements once. So this is the new time complexity. So both will pass. I will encourage you to code both the solutions by yourself before moving forward, because next we are looking at the code, and again coding and getting it accepted is the very must part in any up solving that you are doing, because that would help you retain the concept for a longer period of time. So hope you have at least tried coding it yourself. This is the code. So as we have discussed, there are two possible approaches, one with index and one without index. So I have tried coding them, both of them, and both of them were accepted during the contest. So there is no issue with the time complexity as such. So here we have index, last index, and mask. So what we are doing is exactly similar to what we have discussed. If index is n, I will return 1. Otherwise, I will first check cache. If I have this cached, then I will return that, but I will return that particular answer which I have there in the cache. Otherwise, I will iterate over every element, see if it is already taken. If it is taken, I will continue. Otherwise, I will check whether it is good or not. If it is good, then only I will say that okay, I can put the current element here and I will move forward with the next set of permutation, right? The exact same thing is happening here. Instead of depending upon index, we are just depending upon mask to check whether we have filled every position or not. So inside this loop, again exactly same thing, we are just checking whether it is already taken or not. If it is taken, we'll continue, otherwise we'll check whether it is good or not. If it is good, then only we will say that okay, I can put this current index here, and because I have put current index here, this is now the last element or the last index, and this is the set of already taken elements, right? So hope this entire solution makes sense. If you have any doubts in this particular problem, feel free to post them in the comment section below. I will be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.